find the relative extrema of f of x equal 2x minus 3x to the power 2/3. Our next problem. And we know the routine. We know we need to find the critical numbers because that's the only place these relative maximums and minimums can occur. So to find the critical numbers, we have to know the derivative. So in this case, calculating the derivative of 2x, of course, is just 2, minus 3 times the derivative of x to the 2/3, where we bring the exponent down. And then we decrease the exponent 2/3 by 1, which gives us a negative 1/3. Well, we clean this up a bit. And that's, 2 minus 3 times 2/3, of course, is 2. And x to the negative 1/3 power is 1 over x to the 1/3, which is the cube root of x. And so, again, we clean up a bit more, and this is 2 minus the fraction 2 over the cube root of x. Okay, so finding the critical numbers. Okay, then there's two things we have to consider. Where is the derivative 0? And where is the derivative undefined? Let's first consider where the derivative is undefined, because in this case, the derivative does have a denominator involved in it, the cube root of x. And so the only way that denominator can be 0 is if x is 0. And so the derivative is undefined if x is equal to 0. Now, on the other hand, when we're calculating where the derivative is equal to 0, then that means we're having to deal with where 2 minus 2 divided by the cube root of x is equal to 0. So we've got to solve this equation. And the way we would solve this equation what I would do is I'd multiply both sides or all the way through by the cube root of x. Let's get rid of that denominator. So I have the cube root of x times the left side is equal to the cube root of x times the right side, which is just 0. Okay, so on the left side we'll have 2 times the cube root of x minus just 2 when we multiply with that fraction, and of course equals 0. Now, what we would do to solve this equation is we would isolate the radical so that we can cube both sides and get rid of the cube root. So we'll add 2 to both sides, get rid of the 2 that we have here, and then we'll divide on both sides by 2. So we end up with the cube root of x is equal to 2 over 2, or simply the cube root of x is equal to 1. Now we'll cube both sides so that we can get rid of that radical, and then we end up with this, x equal 1. So this comes back up here now. What we've found is we have 2 critical numbers. The 0 and 1. So we've seen how we handle this. We'll come down here and we'll begin to analyze by testing the first derivative to see if it changes signs as we move across 0 and we move across 1. So we can more or less think of a number line. We put the first critical number, which is 0, and then the second critical number, which is 1. We have them lined up from smallest to largest. And remember how we're going to do this. We're going to first look for the sign of f prime. And so as we're building this table, we're looking to see where the sign changes. Now, let's make sure we completely understand, though. These 2 critical numbers break our number line, if you will, into 2 intervals. From negative infinity to 0, everything less than 0, everything between 0 and 1, and then everything from 1 to infinity, that is everything bigger than 0. And so we begin testing. And so we need to test a number that is between negative infinity and 0. And what are we testing? We're testing the derivative, aren't we? So for instance, we could test a negative 1. And so f prime of negative 1 would be 2 minus 2 over the cube root of negative 1. Well, the cube root of negative 1 is negative 1. So this is 2 minus 2 over negative 1, which is 2 plus 2, which is 4. But most importantly, is positive. Okay, now next we need to test some value between 0 and positive 1. Well, that's a little trickier, isn't it? And I'm thinking to myself, I'm going to have to put a value in for the cube root of x. Then the x I choose is between 0 and 1. So I'm going to make my life easy here, and I'm going to choose x to be 1/8, because I can take the cube root of 1/8. So I'm going to put a 1/8 into the derivative, so it becomes 2 minus 2 over the cube root of 1/8. So the cube root of 1/8 is 1/2. So this is 2 minus 2 over 1/2. Well, 2 over 1/2 is the same thing as 2 times 2 over 1, isn't it? And so that ends up being 2 minus 4, or negative 2. Most importantly, though, it's negative. And this is one of those aha moments. We change signs of the derivative. So that's significant. And what we know, well, we'll come back and look at this all together in a moment. Let's look at the interval from 1 to infinity. And so we might choose something like a positive 8. Okay, it's in that interval from 1 to infinity. We can't choose 1 because that's on the border. See, that we've got to choose it inside the interval. So f prime of 8 we calculate. That's 2 minus 2 over the cube root of 8. And of course the cube root of 8 is 2, so that's 2 minus 2 over 2, or 2 minus 1, which is 1. But most importantly, it's positive. So we had a positive, then we had a negative, and then we had a positive. So we change signs again. So that means we have a relative maximum or a minimum. Now, here's the graph of f, of the derivative of f. Here we know we're increasing. So it's going up. And then here we know we're decreasing. So it's going down. Well, if it goes up and then goes down, it means at this x value of 0, we have a relative maximum, don't we? Change from going up to going down, so it had to be a top point. Okay, we'll come and address that in a moment. And over here we know we're increasing. And so we were going down and now we're going up. If we go down and then up, then at this value, which of course is x equal 1, we have to have a relative minimum, don't we? So we have our information. Relative, let's see, what was the first one? A relative maximum at x equals 0, because we were going up and then we're going down. When it changes from positive to negative, we have a relative maximum. Relative maximum at x equals 0. The maximum is, okay, the maximum is f of 0. And f of 0 is 2 times 0 minus 3 times 0 to the power 2/3. And since everything is 0 there, then f of 0 is 0. So the maximum is 0, and it happens when x is 0. Okay, now, we know we have a relative minimum. When we change from negative, which we have here, negative to positive, it was going down, now it goes up, so we have a relative minimum. Relative minimum, minimum at the x value of 1. The minimum is the y value, isn't it? The minimum is f of 1. So how do we calculate that? Well, let's put it into the function 2 times 1 minus 3 times 1 to the power 2/3. Well, 2 times 1 is 2, and 1 to any power is 1, so it ends up being 2 minus 3, or negative 1. So the relative minimum is actually the value negative 1. Now, we'll look at a graph next to see the graph of this function, to see how this all fits together. And then we'll do an additional problem.
Okay, here you can see the graph of the function that we just analyzed. And to make it clear here, of course, this is the graph of f of x equal 2x minus 3x to the power 1/3. Excuse me, is that 2/3? Pardon me. And when we did our work, let's remember what happened is that we actually found a we found a critical number at 0. Okay, so that x value, and we had found a critical number at 1. And the critical number at 0 came from the x value where the function, where the derivative was undefined. And you see that fits with our graph here. A derivative is undefined where we have a pointed place on a graph, because what really happens there is the tangent line ends up being vertical. So the tangent line is undefined, has a slope that's undefined, hence the derivative is undefined at that x value. But we see that at that x value, actually, we do have a relative maximum because that's a high spot on the graph. And of course, the y value there is the y value of 0. Now, on the other hand, for the critical number of 1, see, we go down and we found out that in that critical number, then we have a relative minimum because the graph was decreasing on the left side and increasing on the right side, as we see here. And so the relative minimum is actually associated with the x value of 1, but the relative minimum is the y value of negative 1 over here. And of course, that's exactly what we found. So it's interesting to see the graph after we've made the analysis. Of course, we didn't know the shape of the graph, but we knew the relative maximum was 0 and the relative minimum was negative 1.
Okay, here we have the last of our problems in this part. Find the relative maximums and minimums of f of x equal 1/16 x squared plus 1 over x. And once again, we don't really know whether...
Well, sorry for that little mix-up. It started the problem over again, but let's now move on.
In this problem, I'm starting it as posing a question, okay? And the question is, for a function f of x, which I haven't told you yet, we have two critical numbers, 0 and 4. So those are the critical numbers. Those are where actually the derivative is equal to 0. Both critical numbers result in a relative extrema. So as we test, we know we have a relative extrema at x equals 0 and x equals 4. Now, we also know that f of 0 is the number negative 2. So the y value that goes with x equals 0 is negative 2. And f of 4 is equal to 6. So the y value that goes with the critical number 4 is positive 6. Which is the relative maximum? Is negative 2 the relative maximum, or is positive 6 the relative maximum? Now, I hope that you probably understand that I wouldn't be asking this question if it was obvious. So here's actually the function. So our problem is going to be this: find the relative maximum and the relative minimum of the function f of x is equal to the fraction x squared minus 2x plus 4 all divided by x minus 2. So that's what we're to do. It's related to the question above. So first thing that we need to do, of course, is find the derivative. Now to find the derivative here, we've got to use the quotient rule. So f prime of x is going to be, let's see how the quotient rule works. Remember, it's the denominator times the derivative of the numerator. And the numerator, of course, is x squared minus 2x plus 4. Subtract, oh, this is long, isn't it? The numerator, which is x squared minus 2x plus 4, times the derivative of the denominator. And of course, the denominator is x minus 2. And all of that's divided by the old denominator squared. Well, it takes a bit of work to go through and simplify this, but I'm convinced you can do the simplification. And after I do the simplification, then I end up with x squared minus 4x in the numerator over x minus 2, the quantity squared, in the denominator. So there is the result of calculating my derivative, which takes a little bit of time, as you understand. Now, our next job is to find the critical numbers. Now, here's the first place that we might have a little bit of trouble. Okay, so remember, there's two types of critical numbers, or there's two types of situations that create a critical number, where the derivative is 0 or where the derivative is undefined. Now, in this case, we have to be careful about this derivative being undefined, because when we look at the derivative, we see a fraction. And of course, a fraction is undefined if the denominator is 0. And so we look at that denominator and we say, well, look, if x was a 2 value, we'd have 2 minus 2 squared in the denominator. We'd have 0 squared or 0 in the denominator. So we might think that we would have x equals 2 as a critical number. That would be our first inclination. I'm going to put a big question mark here. In fact, I'm going to put 2 question marks. Certainly x equal 2 is where the derivative is undefined, but look at the original function. The original function is undefined at 2. So how can you have a relative maximum or a relative minimum where the function is undefined? And so now this was different. We call this a pseudo-critical number, where we're talking about whether the graph is changing from increasing to decreasing or vice versa, when we're looking at increasing and decreasing intervals of a function. And certainly on either side of where a function is undefined, we might change from increasing to decreasing or vice versa. But where there's no way to have a relative maximum or relative minimum at a value that is not even a valid value for the function. X equal 2 cannot be an x value used for the function. So in this case, we don't need to consider this number x equal 2, because we can't have a maximum or a minimum at this undefined place. Okay, so we turn our attention then to looking at where the derivative, which is x squared minus 4x over x minus 2, the quantity squared, is equal to 0. Now, as I've mentioned to you before, the only way a fraction can be equal to 0 is if the numerator is 0. So we're really just needing to know what x's cause that numerator to be 0. And we can easily factor this and get x times x minus 4 is 0. And so the two solutions would be x equals 0 and x equal 4. Those are the two values that would cause the two factors to be 0. Well, now that we know, so those are our critical numbers right there. Okay. Now, here's the next thing we need to decide. Do these critical numbers, and see that's in the problem above, if you see, I said that we had critical numbers 0 and 4, and here they are. Now, the next part of this process, you recall, is that we're really thinking about the x-axis, aren't we? Say, there's the x-axis, and we place 0 on the x-axis, and we place 4 on the x-axis. Now, this actually breaks the x-axis into 3 intervals, from negative infinity up to the value 0, the numbers between 0 and 4, and from 4 to the right forever, that is 4 to infinity. So there are our 3 intervals, and what we really care about is knowing about the sign of the derivative, and from that understanding about the graph of f. And so we test, as we've seen before, okay, we test in each of these intervals to understand whether the derivative is positive or negative. Now, in the case of negative infinity to 0, let's just let me put that down here, negative infinity to 0, these are x values that are in fact negative, aren't they? These are negative values. And so if we look at the derivative, okay, if we look at the derivative for any one of these negative values, what's the derivative? It's x squared, minus 4x over x minus 2 squared. If we choose any value, there's several ways to look at this. Think about if we choose a negative number. Well, that's what we're talking about here. X squared is positive, okay? And let me think of a way to do this. I'm kind of thinking, look, if we calculate the derivative using a negative number, well, we'll have a negative number squared minus 4 times a negative number, and below, 4 times a negative number, my bad, and below we'll have a negative minus 2 squared. Well, up above, that's going to be positive when we square a negative number. A negative 4 times a negative number is positive, so we'll have plus a positive. And below, we're going to have a negative number, but when we square it, it's going to be positive. So that's actually going to be a positive result. Now, we could have actually chosen negative 1 or negative 2 or negative 3 and calculated, and that would have been all right. I was just showing an alternative. Now, in the interval from 0 to 4, we need to pick some value of x that we can calculate to find out whether the derivative is positive or negative. Now, remember, again, why this is going on is that we found critical numbers, and critical numbers are the only places that the graph can change directions. And so all we need to do is find out whether the derivative is positive or negative in this interval, because that tells us whether the graph is increasing or decreasing. And since it can't change directions in the interval, because it can only change at 0 and 4, one test number in the interval tells us about the whole interval. So I'm going to choose the value 1 that's in the interval, and I'm going to put it in the derivative. And so I end up with 1 squared minus 4 times 1 over 1 minus 2, the quantity squared. Now notice on top, that gives me a 1 minus 4, and on bottom, that gives me a negative 1 squared, which is a 1. And so I actually get a negative 3. But what I really care about is that that's negative. And so now we know, since we have a change in sign of the derivative, we have a relative maximum or a relative minimum. Okay, and then lastly, from 4 to infinity, we need to pick some value, or we can just analyze it. But let's suppose that we pick a value like 10 for x. Well, then we have 10 squared minus 4 times 10 over 10 minus 2, the quantity squared. Well, 10 squared is 100, And minus 4 times 10, that's minus 40. And below, we have what? 10 minus 2, which is 8, and 8 squared is 64. And really, all I really notice here and care about is that's a positive on top divided by a positive on bottom, and so that fraction is going to be positive. So I have a change of signs once again. So I know I have a relative maximum or a minimum. Now, in the case when the derivative is positive in this first interval, I know the function is actually increasing. And in the second interval, the derivative is negative, so I know the function is decreasing. And in the third interval, the function is, the derivative is positive, so I know the function is increasing again. So I can draw some conclusions now. And here are my conclusions. At x equals 0, the graph changes from increasing to decreasing. See, at x equals 0, we're increasing, and then we decrease, don't we? That's what this tells us. And so that means that we have a relative maximum at x equals 0. And the way we determine what that maximum is, okay, the relative maximum is the value of, the relative maximum is the value of f of 0. Okay, and f of 0, then, we calculate by putting it into the original function. Now I'm going to tell you, when we put that value into the original function, which is up here, we get 0 minus 0 plus 4, so we get a 4 in the numerator, and we get 0 minus 2, which is negative 2 in the denominator. 4 over negative 2 is negative 2. So negative 2 is the relative maximum. Okay. Now, at x equal 4, look what our chart tells us. At x equal 4, we were on the left side of 4, we're decreasing. And on the right side of 4, we're increasing. See, this is where 4 is. And so, knowing that, we have to have a relative minimum, don't we? A relative minimum. Oops, relative, sorry, minimum at x equal 4. And the minimum is the value of f of 4. Oops, of f of 4. And so we calculate that minimum by putting 4 into the function. And when we do, let's see what we'll get. We'll have 4 squared minus 2 times 4 plus 4, all divided by x minus 2, or 4 minus 2. So in the numerator, we end up having 16, 20 minus 8. We'll have a 12 divided in the denominator by a 2, which is 6. So 6 is the relative minimum. Okay, now, the original question up above, which is the relative maximum? Is negative 2 the relative maximum, or is positive 6 the relative maximum? And of course, here we see the relative maximum is negative 2. And this is uncomfortable to us until we see the graph and understand. And it is important to understand that we can't tell by the value of a relative minimum or a relative maximum which is which. We can only tell by whether the graph is changing from increasing to decreasing or decreasing to increasing. Relative maximums or minimums are about the behavior of the graph, not actually the lowest or highest place on the graph. So let's look at the corresponding graph to this before we go on to our last problem.
here you see the graph of the function that we were just analyzing. And remember, at x equals 0, which is right here, at x equals 0, we found out that we had a relative maximum of -2. Okay, well, that's associated with this y value, and it's a relative maximum because to the left of 0 we were increasing, and to the right of 0 we were decreasing. So that makes that a relative maximum. Of course, that whole point is lower than this point, which is a relative minimum point. We had the critical number 4, and at 4 we found out the function was decreasing to the left of 4 and increasing to the right of 4. So that makes this position a relative minimum, and that relative minimum is a +6. So here we actually have a maximum, relative maximum, smaller than a relative minimum. And once again, it doesn't have anything to do with the values of y here. It has to do with the behavior, changing directions, and having a maximum position relative to this part of the graph, and a minimum position relative to this part of the graph. So we have to be careful. Again, relative maximums and minimums are about the behavior of the graph, not the highest part on the graph or the lowest part on the graph. Well, let's move on now.
Okay, in our ending problem here, we go back to the very beginning of the section where I pose the question, in a 30-second commercial, when is the best time to present the sales message? Well, here's the entire problem. I'll read it to you. Suppose that a manufacturer of a diet soft drink is disappointed by sales after airing a new series of 30-second television commercials that it made. The company's market research analysts believe that the problem lies in the timing of the message, and that message is drink sparkling light. They've decided either it comes too early in the commercial before the viewer becomes completely involved in the commercial, or it comes too late after the viewer's attention has faded. After some experimentation, the research analysts find that the percent of full attention that a viewer devotes to a commercial is a function of time in seconds. So that is a function in time since the commercial began. Where you see this function below, the viewer's attention is the f of t, is the y value, and it's equal to -3/20 times t squared plus 6t plus 20, where t is the measurement of time in seconds from the beginning of the commercial. Now, this is a 30-second commercial, so t could be as soon as 0, but no later than 30, and of course it'd have to be less than 30 to get that in. Okay, so when is the best time to present the commercial sales message? Well, remember what we want. It's unsaid here, but what we want is the message at the time of the maximum viewer's attention. Maximum viewer's attention. And so what we're actually wanting to know is the value of t that gives us this maximum. The value of t, because we want to know when to put the message. The value of t that gives a maximum in this function. And so the way we've done this in the past is we're really looking for a relative maximum of the function f of t. So we find the derivative, and we see that the derivative is -3/10 times t to the first power plus 6. And we'll write that just a little bit differently. We'll write that as a -0.3 t plus 6. Now, to find the critical numbers, see, we're looking for a maximum or a minimum, but we're looking for a maximum. So to find the critical numbers, okay, and in fact, I think there'll probably just be one here. The critical number, is when f prime of t is equal to 0, or negative 0.3t plus 6 is equal to 0. Now what I'm going to do here is I'm going to multiply through by a 10. Okay, I'm going to multiply by 10 on both sides. Why? To get rid of that decimal 0.3. So I've got to multiply all parts by 10, don't I? Whoops, by 10. And so we end up with negative 3t plus 60 is equal to 0. Now we're solving for t, so we'll say negative 3t is equal to negative 60, and when we divide on both sides by negative 3, we get t is equal to positive 20. Now, here's what we need to know is at this value of t, now that represents 20 seconds into the commercial, at this value of t, does it give a maximum viewer's attention? That is f of t at a maximum? So we set up the testing mechanism for t equal 20 as our critical number. We have the interval from 0 to 20. Remember, t is not going to be less than 0. And we have the interval from 20 to 30. 30 is not going to be, the t is not going to be bigger than 30. So it's only a 30-minute commercial, a 30-second commercial, pardon me. And so now we're going to do our testing. And we're testing the derivative, okay, at these values. So for instance, in the interval from 0 to 20, what we would find out, let's just calculate, maybe f prime of 10. Well, remember, our function is negative 0.3 times our t value, in this case 10, plus a 6. And that ends up being negative 3 plus 6, which of course is positive 3. Most importantly, it's positive. And then we need a value between 20 and 30, and I suppose we could try 25. Okay, so we'll say, what's f prime of 25? And f prime of 25 is negative 0.3 times 25 plus a 6. Well, negative 0.3 times 25 is actually negative 7.5. And when we add 6 to that, we get a negative 1.5. But most importantly, it's negative. So what we really see is that in this interval, the function is increasing. That is, the viewer's attention is actually increasing, okay? And in the interval from 20 to 30, the function is decreasing. So that means the viewer's attention is decreasing. And so we want then to choose t equal 20. That's actually going to be our maximum attention span, isn't it? A maximum attention of the viewer, maximum viewer's attention. And we've decided that, of course, because we were increasing and then we began decreasing when we passed t equal 20. So the answer here is that we want the commercial or the message should appear for the maximum viewer attention 20 seconds into the commercial. Pretty fancy, isn't it? Now we see how market research can pay dividends. Well, that's the end of this section. I hope it's been helpful. We'll stop this and allow you to begin your homework.